back on the other board, we were just summarizing some relationships between proof systems. So the syntactic things that are usually consist of trees of symbols, um, usually consisting of deduction rules, and semantics. And so one of those properties is soundness, which is usually expressing something like so if you've got some set of formulas gamma and uh, some formula phi semantically follows from it. Sorry, not this is the wrong direction. Uh, if in your proof system uh, there is a proof which deduces phi from that set of sentences, then there's a semantic entailment. So in any model satisfying all the sentences in gamma, in any of those models, phi is also true there. Sorry, there's just a printer going behind me.
I was gonna say, yeah, what is that? But yeah,
Yeah, someone's printing something in the office I'm in.
no problem.
Sorry. Is it? Could you hear what I was saying?
I can hear it. I can also hear the printer, but it's not terrible.
Okay. Okay, great. It's done. um, and so I was claiming that the idea of this is that it says uh, the proof system says correct things about the semantics. Um, and Dan, you proposed that like another reading is where like the proof system is more fixed. Is that maybe you're choosing the semantics, and some choices of semantics might not be sound, and some will be.
Yeah,
Um,
that's right.
okay. Uh, Another one is then completeness, which is the other implication. That if you have semantic entailment, then you have uh, then your proof system can sort of recognize that and prove uh, improve phi from the set of sentences gamma. Um, yeah, and so this, I guess, the way in light of the seminar so far, I think a good way to that I like to think about this is uh, I kind of think of the deduction rules uh, as they're all like they sort of there's interplay between the deduction rules, and when you have more deduction rules, there's more possibility of producing conclusions from proofs in the proof system, and um, and when you're complete, a sort of so a corollary of completeness is if we put falsity in place of the formula phi, uh, it's saying that a complete proof system can recognize inconsistency in the formulas. So if there's some inconsistency in the formulas gamma such that no model can satisfy all of the formulas, and so it's saying that uh, you're able to like the deduction rules allow you to sort of smash the formulas together um, in enough ways such that you can produce a proof of inconsistency.
Well, that seems to be different to what you said, though. You said no model. There's no. Supposing there's no model of gamma, is that literally what gamma funny turnstile falsity means?
Yep. So I guess
I mean, it
it's
implies
actually
that there's no model, but is it also implied by the non existence of a model?
Wait, is what implied by the non-existence of a model?
Okay, the way. How do we say this turnstile with the extra arrow, the extra line?
Uh, I think I usually just say entails.
Entails, okay. So gamma entails falsity would mean that whenever gamma is true, well, what is this? Sorry, remind me what
So
this would.
gamma is a set of formulas.
Yeah, so remind me what this entailment means when you have falsity on the right hand side.
Yeah, so it's the funny thing is that with uh, it's actually a bit more. It's easier to define not entails, as in so to define uh gamma doesn't entail phi is really what that's saying. Like you could take this as a definition that um, there is a
Oh, sure. Yeah.
model M of uh, M union not phi, and so uh, then you can say that this entailment means not
Yeah. All right.
this. That's where I get there's no model of there's no model M of all right, I wrote M there again, but it should say gamma. There's no model of gamma union not false, i.e., there's no model of gamma. That's where I get it from. Um, so what I was saying is that uh, so soundness and completeness with respect to like what deduction rules you have present. Soundness is sort of it gets well, let me say completeness first. So completeness sort of means uh, that you've added enough deduction rules. Um, whereas so I'm viewing like an incomplete proof system as one which has like not been opinionated enough to recognize inconsistencies. Um, and so this is what happens with uh, second order logic, I believe, is that when you have a when you have a you can't have a sound proof system in second order logic which is uh, effectively computable and also complete. And this is where it goes into the realms of some of things that don't quite haven't quite mapped out yet.
So, what does second order logic mean?
Yeah. Okay. So that's a good idea. We should talk about that. Let me just go to the second board. So in first order logic, you can in first order logic, what happens is you start with your language L, which has constants, um, constants A, B, C, and so on. So in piano arithmetic, you just have a single constant for 0, and you have function symbols and so on. Not too important, but usually you have just some small fixed choice of predicates, or I guess in the terminology of this seminar, you have relation symbols. So P, Q, R, they're usually with capitals. And so in what's an example of a relation symbol? You might have like X is less than Y or something, for example. That's a two-place relation symbol that I've written with infixed notation, but you could think of it as like uh, as LXY, but just written differently. Um, and so in first order logic, you're sort of fixing just some usually small choice of some predicates that express uh, that express like the sort of relationships between objects that you're going to axiomatize with your first order theory. Um, but in second order logic, you uh, you allow uh, you allow quantification over these things. So obviously, in first order logic, we have things like for all x, uh, p of x, and that's quantifying over the sort of objects in the domain of the model. Um, but in second order logic, you can sort of add on uh, exists p. So you can say uh, there exists a predicate p such that for all x, p of x. Um, and so this is where like uh, there's a question to be answered of like what's the semantics of this, and there's a few different choices. Um, so there's two questions. There's what's going on the semantic side of things, and then what is going on uh, the sort of the proof theory side of things. What are the sort of deduction rules involved? Um, and so, for example, okay, on the semantic side, there's what's called the full semantics, and what happens here is you have. Let me just think about this. So you have your domain D, which is just your set of objects, and the variables and all the terms. These terms here, they range over that domain. They get interpreted as things in that domain D. And then there's the sort of domain for predicate symbols as things that predicate symbols get interpreted as. And I guess it would be something like for each n. I'm not familiar with like the right notation for this. I guess I won't give it a name. You want uh, the sort of domain for the n place predicates is the power set of D, the power set of D to the power of N.
Mm-hmm.
And so those are, yeah, so a predicate is like it can be interpreted, is usually interpreted as a set. And so in the full semantics, we're saying when you specify a domain, the the domain of predicates is just like every possible like predicate um, that's a sort of, yeah, every possible predicate on like uh, n objects from D. Um, so that's the full semantics. And I guess the other semantics doesn't make sense until you talk about the proof system side of things. Um, so here is uh, here's the here's like the deduction rule that you would come up with for second order logic. Let me actually just find my reference for this and I'll just copy it from there. So this is it's an instance. This is an instance of the comprehension uh, schema, or maybe it's just the comprehension rule. I don't know. Um, so we wanna be able to make deductions like this. So if phi holds of x1 up to xn, uh, then we should be able to prove from that. I guess I can write it as a deduction rule. Exists R holds of x1 up to xn. I think I'm getting that like intermittent lag every now and then when it does a big garbage collection. Um, okay, so this comprehension rule. So this is saying you can deduce the existence of some predicate R.
So now
satisfying like
now there's like propositional variables in addition to kind of, I don't know, what's the difference between phi and the R? The R is now a kind of new kind of variable, correct?
yeah. So I should say that. So like you would think of it as like, I guess I wrote relation symbols here with R as an example. But yeah, there are sort of your constant predicates if you've sort of determined some in your language, but then there's also the like variables. There's like predicate variables.
But you can also, I mean, it's not just constant predicates. You can also presumably construct new ones from old ones using logical operations and so on,
right? What do you mean?
Well, x less than y or x less than z. It's a three-place predicate.
And so what are you asserting about that?
I'm saying phi could be such a thing, right?
I think actually, so this is, let's say in this example here, phi is just like a, I shouldn't have wrote phi. I should have. I want to say this is just like there's just a regular predicate symbol p, and this is just an atomic formula here with n. It's an arity n atomic formula. Uh, I'll now write the more general version of this rule, which is if you've got any formula at all phi, and um, let me just write out what it says. Lambda x uh, below its exists R phi, where phi square brackets stuff denotes the result of replacing every atomic formula of the form R T1 up to TK in phi by psi T1 up to TK. I'm just trying to think about what this means. Does this apply to the example you were just giving?
Yeah, it's effectively what you said before. It's just doing it inside something. So what you gave is a special case of this where isn't that right? So you reach inside phi, and then if someplace you see. Wait, no, that's not right. I don't understand this rule. This is very strange.
It's a result of replacing every atomic formula of the form R1. I think the notation makes
No.
sense if it's like this.
Can I ask a question?
Sure.
Okay. So the first order is about relationships, and the second order is about relationships being enacted or quantified, I think you said, on a collection. Then from that, you're going to draw a comprehension rule based out of your second order. Is that the way this is flowing, roughly?
I would summarize it as in first order logic, you have some fixed relations that you can express about objects.
Okay.
And you can quantify over those objects and sort of express relationships between those fixed relations by quantifying over objects. Like I'm talking about something like for all x, p of x implies r of x or something. So you can quantify over objects. Here, instead of just having some fixed collection of uh, relations that you can talk about, you can sort of quantify over relationships in the abstract, and that in that you could talk about any relation on objects.
Nice. So might an analogy be, say, the development of the periodic table, where we start with some relationships, develop out elements, and then look really at the structure of the table, and then begin to realize that the the table isn't complete, we can return to it and begin to realize that we have other elements that are probably out there that will fit within this structure and work through generative logic that way. Kind of like more recent example in physics, the Higgs boson, right? Where what we're looking to do is find symmetry that would ultimately be our comprehension. And then what we have to do is fill in where we're missing a certain kind of particle or whatnot to make our structure ultimately complete. Is this going in that direction somewhat?
Maybe in the case of the periodic table, you could think of you could say the structure of the table itself would encode, it's kind of a first order logic. There's some definite relations. I suppose if you had some knowledge, what's a form of knowledge that it would be difficult to encode in first order logic? Well, it might be something like, if there were some new relation between elements in the table, I'm not saying what kind of relation it is, but if there were a relation like that and it holds for everything in a column, then it must hold for everything in the next column. Right? Suppose you know something about the process of going from one column to another, and it's so strong, this relationship between columns, that any abstract thing that kind of holds among the first things in the first column must also hold among the things in the second column. That's a kind of meta knowledge from the point of view of the first order theory, but you can express it using the second order theory by saying that any relationship among things in column 1 must also hold among things in column 2. For example, going from row to row. I actually forget how the periodic table works, but suppose you're adding electrons in the outermost orbital by going down. I forget if that's correct. But that's a relation. But maybe you know any relation of that form would have to hold for column 2 if it holds for column 1. But that would be a statement you'd make by quantifying over relations. I don't know if you'd agree with that, Billy, but it's the best I can do with the periodic table, I think.
Yeah.
So essentially, we start with the structure of the periodic table, and we could say that was the first order logic. And then as we realize we're not really complete, right? We could use this kind of structure to work through it. So what would be the second order?
So I should say first that first order logic as the system of proof and the semantics, it is complete. So the completeness theorem holds. So like there's a specific kind of incompleteness that we're like attempting to fill in the gap, and maybe I'll give a more concrete example, and that might inform the sort of comprehension story a bit better. So we have there is the what is it called? So there's in piano arithmetic, you have some basic expressions that you can make about about in piano arithmetic. It starts with just a bunch of very simple properties of addition, successor, and multiplication, and then there's this axiom schema of induction. And I'll say, I guess, where I'm going is that, yeah, there is a sort of first order logic can sort of talk about some collections, but yeah, as we were saying, the fact that it can't reason about collections in the abstract prevents it from expressing certain things about the domain. For example, it cannot express just the property that like there are finitely many things. You can express that there are like 4 things, or that there's 5 things, or that there's 6 things, but you can't only say that like there's finitely many things. So in general, first order logic struggles with declaring like things about collections of things. It can do some collections of things, but not all of them. And so let me write down the axiom schema of induction, or what it sort of looks like. It's saying it starts with like it looks very second order, because it does start with for all phi, and here, and this is what makes it a schema. I'm not actually writing down a single axiom. I'm writing down like, here is a recipe for creating a first order formula. And actually, I should actually indicate it as such. So the for all phi is not actually part of the formula. It's sort of an external quantification.
And that's making sense, right? So your original intuition is the structure of the periodic table, but that intuition doesn't ultimately tell you how many elements you have. You have to work through second order logic to begin to understand what the completeness of the table itself is going to be, right?
Yeah, I don't know if completeness is the right way to think about what the difference is between first and second order logic. I think
Okay.
it would be more appropriate, perhaps, just to say that there may be you may have forms of knowledge.
The question to ask is, what can't we express, and why do we want to express it? And like, so we're looking for that line. So I can eliminate that. So axiom schema of induction for a formula phi, which just has a single variable sort of hole to fill in a term, is phi holds of 0, and for all x, if phi holds of x, then phi holds of the successor of x. Okay, so just using these these axioms here are sort of, we're quantifying over. You might think we're quantifying over all properties of x, but we're only quantifying over the first order expressible ones. And so it's not the so it's this set of all subsets the set of all subsets of natural numbers. Let me think about how to express what I'm saying.
I don't really understand what this line means. So I get the induction axiom schema, but then this set is a set of formulas, not a. So what's the PA? Oh, that's the set of sentences in piano arithmetic. Okay, yeah.
Yeah, this is I'm. Yeah, I mean this as the set of axioms of PA. Yeah, so you're throwing in infinitely many axioms into your set of axioms, but it's all still computable because you can compute whether or not an axiom is an instance of this schema, or if it's any of the other axioms. Yeah, and it's so this, when you interpret if you take a particular formula phi, You can think about the set of all you can think about the set of all I don't know how to write this, but the set of all elements of the domain that satisfies this formula phi. When you
Otherwise called X such that phi from the comprehension.
Yeah.
You're saying that set of subsets of n is not all possible subsets or something.
Yeah.
Yeah.
And that's what makes this axiom schema of induction. That's what allows the sort of incompleteness of arithmetic or any theory, first order theory that extends arithmetic, to be complete. It allows the models to not just be like it allows the models to be like non-standard and not just like the regular set of natural numbers. Whereas if your proof system can express for all phi and then like fill in the axiom schema there, but with this I guess not phi, it should be like just for all r, and then the semantics of that is saying that like r could be interpreted as any subset of the natural numbers. Then you do actually like the only possible model in that case that satisfies this formula and the other Peano axioms is the standard natural numbers. But clearly, so the issue is that you can't like. There's no deduction rule that allows you
so
to.
This is because you can always take the relation that says you're equal to 0, and then another one says you're equal to 0 or you're equal to 1, and another one says you're equal to 0 or 1 or 2, and by quantifying over all relations, you could somehow cook up is it a secret way of having an infinite disjunction of that form by quantifying over relations? Is that the trick?
I think it's a bit simpler than that. I think you can say you can more just directly. All right, I found a claim that you can express all these things in second order logic, and together their only model is n, which is you have they're positing it as the second order theory in the language that also has less than or equal to, but we can construct less than or equal to with plus and successor. We can make a formula out of that. Anyway, they say the three axioms. So the set, the domain with the with less than or equal to is a linear order without a maximal element. Every non-empty set has a minimal element, and every bounded set has a maximal element. So you just make claims about all collections. Yeah. So actually, those every non-empty set has a minimal element. I think that itself is just expressing. I think that's equivalent to like the axiom of induction in the sort of second order form.
I mean,
So it's
when
not
you
like
say when you say every set, you mean every relation.
Yes.
Right. So you say for all R, blah blah blah, and the things for which R is true is the set you're talking about.
Yeah.
Hmm.
So the axiom schema of induction is just that second axiom that every non-empty set has a minimal element. So yeah, it's not an instance of the rule. It's like the whole rule that, like, it's only possible, like, you have to be the standard set of natural numbers. Yeah, so the comprehension rule is only able to sort of derive existence of, like, say in this case, existence of a relation when you can prove a first order example of a relation, something that can be expressed with a first order formula. And that's basically what makes it so that the full semantics, where the set of things that the relation symbols and the relational variables can be interpreted are just like any possible subset. But you can, like, if you take the a different semantics, which is essentially something like just enough to satisfy the comprehension rule, then then you end up with a semantics which is complete with respect to your system of proof, which is just all the first order deduction rules plus this comprehension rule.
I think we should wrap up in a few minutes.
Okay. Will was, I guess, I'm just recalling what Will was saying last time about, like, I got to the end and I said something about okay, so what was I saying? First order logic, it's sound and complete, but we can't ever, like, we're not able to say we can't pinpoint just the standard set of natural numbers without letting go of completeness. And I guess his claim was like, all right, why not
Except the freaks. Yeah.
And I guess like so I think he was saying something about, like, okay, can you have, like, you might have a theory which is not inconsistent, and there it's in the sense of there's no, like, finite proof that gets you to falsity, but that doesn't, like, because you don't have a complete logical system, you don't know that guarantees there to be a model. And, like, so then maybe you sort of justify the I don't know, you justify the existence of a model in some other way. I don't know, I'm interested in, like, where you would go with that, because like what I was saying earlier about, like, the point of completeness is that, like so, like, when you have a sound proof system, like, you could just be really, like, your deduction rules could just be, like, very non-committal, like that they could just, like, uh they could just say, like, a few uncontroversial things. And completeness is a way of sort of, is a standard that you can reach to say, like, these deduction rules are saying enough things and there's, like, enough interaction between these deduction rules. And so when you don't have completeness, I think you need to have some other, like standard for like what is the standard in place of that says like there is enough interaction between the deduction rules?
Well, I don't presume to know what Will had in mind, but well, I mean, from the kind of programming language point of view, it's not unusual to have a system that is, in some sense, sound but not complete. So, actually, it's an
right. What does that mean for programming?
Well, it would mean that you're driving a machine that can do more things than you can trigger with your interventions, but that's okay. So, for example,
Does that mean like then you've got some sub language within your computer that can only execute certain programs, but is it like there's things the hardware can do in terms of the electricity running through it that like
yeah, for
you
example,
can't get it to do that with the language, or what?
or you could just have, suppose you're working in a domain-specific language that compiles to C, but it's not Turing complete. You know, you can do things in your proof system or your programming language which are sound. They all do the things they're supposed to do, but the system can know more things about your programs and what they're going to do, and can do more stuff than what you can trigger with your limited language. Another example where this is an active research topic, maybe it's been resolved now, is something called ZX calculus. It's a kind of quantum programming language where you take the language of finite dimensional Hilbert spaces and quantum gates and so on. And people had some diagrammatic language for writing basically programs. So there's a diagrammatic syntactic thing which maps to actual programs, sort of linear maps between Hilbert spaces, and they could prove it was sound, but they didn't know if it was complete. They didn't know if there was enough stuff in their logic to capture what was possible in the physics. And that's, from one point of view, very frustrating. But from another point of view, well, if you can do the things you want to do with the logic, maybe you don't care that the physical system you're implementing it on can do more things. Or you could have, I mean, the problem is you could have, say, two constructions that are equal, two programs that have the same output for every input, or some rearrangement that is semantically correct, but you can't deduce it. And that would be an obstacle if it's a move you want to make. But I guess I see Will's point as being that, well, maybe I'm willing to give up that completeness, and you can't stop me, or something like that. So I don't. Maybe he had more. That's what I understood him to be saying, but maybe he had more to say on that. But yeah, I think we should wrap up. I have to go, but that was valuable. Thanks.
Cool. Thanks. Thanks for bearing with me. I wasn't really super prepared, but
yeah, I think that was worthwhile.
I think it's good to. It would be good to have Will around because, I think he's very helpful in these discussions. But I think it's a good idea to have more like unscripted, or like not like a typical lecture discussions in foundations, because we usually like do some kind of formal lecture and then have the interesting discussion at the end.
Yeah, I agree with that. I think that's true of all the seminars. Actually, there should be something like weekends. Like every 4 seminars, you just have a weekend where it's just a kind of general.
I think that's a good idea.
Discussion.
All right, thanks.
Yeah, thanks, Martin, and see you next time.